understand the bottleneck in artificial intelligence, you have to look at where the data lives versus where the processing power is being built. Enterprises have spent well over a decade consolidating petabytes of proprietary data into hyperscale clouds like AWS and Azure. Now, those same enterprises want to build retrieval-augmented generation agents or train custom large language models. The most cost-effective place to do that is often outside traditional hyperscalers, using specialized GPU-as-a-service Neoclouds, offering cheaper, available, high-end compute arrays. The friction comes when they try to connect the two. Moving massive volumes of proprietary training data from a legacy cloud environment to a specialized GPU provider requires crossing the public internet. Standard hyperscaler data transfer to the public internet costs roughly 9 cents per gigabyte. When a company moves a single petabyte of historical data for LLM training, that per gigabyte rate scales up into a $90,000 egress fee. Cost is only the first friction point. Training a custom AI model requires moving highly sensitive intellectual property. Exposing that volume of proprietary corporate data to the public internet introduces severe risks of interception and DDoS attacks. The result is a lock-in problem. Enterprises are blocked by egress costs and security constraints from using the broader ecosystem of alternative AI compute. They are tied to the data gravity of their current hyperscaler. PacketFabric's infrastructure provides a direct workaround. They operate a network-as-a-service platform designed specifically to bypass the public internet penalty using dedicated on-ramps. On the left, public internet traffic constantly triggers high fee counters as data exits the hyperscaler. On the right, a private Layer 2 circuit using services like AWS Direct Connect forms a direct pipeline that entirely avoids the public grid. By routing data through this private circuit, the AWS egress rate drops from 9 cents down to roughly 2 cents per gigabyte. For an enterprise executing a massive data migration to a Neocloud, that private connection slashes the total egress fees by 70 to 77%. Because the data travels across a physically separated optical network, the intellectual property remains completely isolated from public internet vulnerabilities during transit. This aligns with PacketFabric's original mandate to treat global telecom infrastructure exactly like elastic cloud compute. Network connections can be spun up and scaled dynamically to enable frictionless data movement. By bridging the gap between legacy data lakes and specialized GPU hardware, the savings from this Layer 2 arbitrage effectively cover the cost of the network infrastructure in a single AI data migration project. The foundation of this system is a massive software-defined network. PacketFabric operates a private optical backbone, a dense wavelength division multiplexing network with over 70 terabits of capacity. Customers connect into this backbone by purchasing a physical access port at an on-net data center or cloud on-ramp. Using Ethernet Virtual Private Line, or EVPL technology, that single physical port can be subdivided into dozens of distinct, isolated virtual circuits. One port can simultaneously maintain separate private connections to AWS, Azure, a private data center, and a GPU provider. Historically, securing these types of telecom circuits required inflexible contracts and a 60 to 120-day provisioning cycle. Because these circuits are virtualized, they can be provisioned and activated in minutes. PacketFabric also supports flexible consumption models. Customers can use burst illing to handle massive temporary data migrations for specific AI training runs, paying only for the exact bandwidth they consume while the job runs. Platform engineering and DevOps teams do not have to manually configure these pathways. They manage the network as code, orchestrating multi-hundred gigabit cross-connects entirely through REST APIs or a native Terraform provider. This combination of optical capacity and API orchestration turns physical telecom infrastructure into an agile, on-demand utility. Moving packets directly from point A to point B solves the bandwidth problem, but enterprise AI workloads require complex multi-cloud topologies that pure Layer 2 transport cannot manage alone. This diagram shows the PacketFabric Cloud Router dropping into the architecture. Instead of requiring the customer to own and maintain physical routers in every colocation facility, Cloud Router establishes a distributed Layer 3 mesh, handling the BGP sessions to link multiple cloud environments together. To expand access to this core, PacketFabric merged with Unitas Global. This added the necessary first-mile and last-mile connectivity, extending the network's reach to over 900 data centers and 50 million enterprise-lit buildings globally. Unitas brought another critical asset from its prior acquisition of INAP's network business, the Managed Internet Route Optimizer, or MIRO. MIRO is a patented routing software that dynamically probes the internet. It automatically adjusts BGP routes in real time to find the fastest, lowest latency paths available. When an enterprise deploys an AI agent to a retail branch or a distributed workforce, inference speed dictates the user experience. MIRO's route optimization shaves critical milliseconds off database queries, ensuring real-time AI responses at the edge. Through this specific assembly of acquisitions, PacketFabric built out the required layers, routing intelligence, edge access, and a massive optical core to deliver a complete AI data network. Adapting network infrastructure for AI workloads is highly competitive, and Megaport has established the industry benchmark for this transition. Megaport has secured massive infrastructure contracts requiring hundreds of millions of dollars in capital expenditure. They are directly procuring NVIDIA GPUs and high-capacity storage arrays to build out their own globally distributed AI exchange and inference cloud. Becoming an AI compute provider introduces a completely different economic profile. It requires managing severe supply chain bottlenecks, ensuring continuous hardware utilization, and taking on the risks of rapidly depreciating GPU hardware. PacketFabric has opted for an alternative approach. Instead of buying hardware, they operate with strict neutrality, acting as an interconnect layer among enterprises and multiple independent compute providers. They partner directly with specialized GPU Neoclouds, such as Massed Compute. Customers can discover and order GPU resources through the PacketFabric portal without PacketFabric taking ownership of the physical servers. Because the network layer remains agnostic, the enterprise maintains total flexibility. They can route massive datasets to one Neocloud this month for H100 access, and dynamically switch to a different provider next month based on better spot pricing or architecture compliance. While Neoclouds often lack the enterprise trust and data adjacency of the major hyperscalers, PacketFabric's capital-light marketplace model solves that exact deficit, connecting stranded corporate data directly to alternative compute. The technical capacity of the network only matters if it can be easily bought and deployed by Fortune 500 network engineers. The next phase involves packaging this infrastructure into concrete AI data fabric products. Instead of manually assembling connections, enterprises will use pre-built templates for standardized routing. For example, instantly provisioning a secure line from an AWS region in Los Angeles to a specific GPU cluster in Ashburn. Large workloads also require staging zones. By reviving capabilities from its RStore acquisition, PacketFabric can offer private object storage and data caching physically adjacent to the GPU clusters, eliminating the need to move entire petabyte databases for a targeted fine-tuning run. This reference architecture illustrates a private RAG flow. The enterprise keeps its proprietary data safely stored inside an AWS vault. The data traverses the private network layer, hits a Neocloud GPU purely for an inference calculation, and the result returns securely to the enterprise endpoint. Because this architecture provides explicit routing paths, reserved bandwidth, and detailed observability, it meets the strict compliance and audit requirements demanded by the healthcare and financial sectors. These standardized templates translate a complex, multi-layered programmable network into ready-to-deploy infrastructure for enterprise AI. The massive investment currently pouring into specialized GPU capacity has a physical limit. Those processors sit idle if enterprise data cannot reach them securely and affordably. PacketFabric removes that friction by executing explicit, multi-cloud private routing that drastically reduces internet egress exposure. The next evolution of the platform will integrate these capabilities into an AI-native interface. A network engineer will be able to type a natural language prompt, instantly generating a validated multi-cloud topology map, complete with security parameters and an exact price quote. The goal is to decouple enterprise artificial intelligence from hyperscaler captivity. Data can remain where it currently lives, while computing power is sourced from the most efficient provider. Understanding this architecture is how you help enterprises bridge the gap between their legacy corporate data lakes and the next generation of hardware. PacketFabric serves as the definitive private data movement layer, providing the dedicated infrastructure required to scale the AI economy.